Alright, so let's talk about the integrating factor method. The starting point for the integrating factor method is that we have a differential equation which is first order and linear, and it's been written in standard form. So dy dx plus py equals to q. Here p and q should be functions of x, alright? Then here's how the integrating factor method gets started. We define this mu, which is the integrating factor. It's equal to the exponential of the integral of p of x dx, which is kind of a weird thing to define, but let's see what it does for us. You notice that when we differentiate this, we're differentiating an exponential, which of course gives us the exponential back again, and then we have to differentiate the inside. But when you differentiate an integral, well, you just get back the integrand. So we get p, and then, well, but hey, this is just mu again. So we find that d mu dx is equal to mu times p. So if we multiply the differential equation that was given, this guy, right, multiply that by mu, we get mu dy dx plus mu py equals to mu q, which I've written down here. All right, so in other words, this, but mu p, remember, was d mu dx. So we've got mu times dy dx plus d mu dx times y equals to mu q. Hey, but the product rule comes into play, right? So we do the product rule in reverse and say that's d dx of the integrating factor times y is equal to the integrating factor times q, which then we can separate and integrate. All right. So, and in short, I mean, we have this formula that's pretty general. 1 over mu times the integral of mu q dx. This is the summary of the integrating factor. Now, I'm not suggesting you actually use this boxed formula to solve problems. It will not work well. We have to actually go through this derivation we just went through for specific problems. Let's see how it goes. All right. Suppose we wanted to solve 1 over x dy dx minus 2y over x squared equals to x cosine x. We know we can solve it once we put it into standard form. So we do that. So in other words, I multiply this by x. Multiplying by x gives me dy dx minus 2 over x times y equal to x squared cosine x, right? So the integrating factor mu is the exponential of the integral of p. Don't lose that. That minus is critical. If you ignore the minus, it'll be wrong. Anyway, so that minus I keep, I integrate, I get minus 2 log of the absolute value of x, which gives me log of the 1 over absolute value of x squared, which simplifies to 1 over x squared. So that says that the integrating factor here is actually 1 over x squared. So we go back up to the original, well, not the original, but the next to this differential equation here, and multiply that by 1 over x squared. All right. So multiplying by 1 over x squared gets me to that, which, if you do the reverse chain rule, product rule, you can see that the derivative of 1 over x squared y is equal to that. Whoa. That's surprising, right? Well, that's the method. If you do it right, you got to be able to think through going from here to here. Think about differentiating that. I get 1 over x squared times dy dx minus 2 over x cubed y, right? And, all right, so once I get that, then I can just integrate both sides. Integrating the left-hand side just gives me the thing being differentiated. And integrating the right-hand side gives me sine of x plus a constant. And so solve for y. There you have it. Notice that if we had not calculated the integrating factor correctly, then we would not have been able to make the reverse product rule work. So that's the check and balance of the method. If you're paying attention, you'd have to make a pair of errors simultaneously to get it wrong. Right? Now, next up we've got y dx dy equals to 2x plus 5y cubed. Now this one's kind of funny because it's making x the dependent variable and y the independent variable. Just wanted to show you that you could do that. It's the same pattern, just replacing x and y's roles. So here mu of y would be the exponential of the integral of 2 over y, which works out to y squared. Again, using that law of exponents, 2 times log of absolute value of y is log of absolute value of y squared, which gives us absolute value of y squared, which is just y squared. And so I multiply the differential equation in standard form by the integrating factor. It gives me this. Reverse product rule gives me that. And so I integrate both sides with respect to y, and I get that. There you go. So here's another one. We've got dy dx minus y equals e to the 3x. So observe, we've got p equals to -1, we've got q equals to e to the 3x. You calculate the integrating factor, mu x equals exponential of the integral of minus p dx, which here is just -1. This gives us e to the minus x as our integrating factor. We multiply the differential equation by that. That gives us e to the minus x dy dx minus e to the minus xy equal to e to the 2x. Reverse product rule tells me that this is d dx. You think, look at that, if I differentiate that, I get that, right? And then once I have that, I integrate both sides. I get e to the minus xy equals to 1/2 e to the 2x plus c. And then I can solve for y if I want to find the explicit solution. There it is. Now, one of the things you might have noticed here is that I have not been adding constants to the integration for the integrating factor, and there's a good reason for that. If we did add a constant, it would just correspond to multiplying the whole differential equation by e to that constant, and that would just cancel out anyway, so there's no need. Here's another example. So dy dx equal to y over x plus 2x plus 1. So first of all, put it in the standard form, right? Identify that p is -1 over x. So I calculate the integrating factor, and I get 1 over absolute value of x. I'm going to assume that x is positive here, so the absolute value of x is x. And so after I've done that, multiply by x, I get multiply by 1 over x, right? So I get 1 over x dy dx minus 1 over x squared y equals to 2 plus 1 over x, because this times that gives me that. And so reverse product rule, integrate both sides. That gives me 1 over x times y is equal to the integral of 2 plus 1 over x, which of course is 2x plus log of the absolute value of x. Since x is positive, we can drop the absolute value, and we get y is equal to 2x squared plus x log x plus cx. Again, I cannot emphasize enough that you have to add the constant when you integrate both sides, and because otherwise, if you don't do that, you're not going to track through the fact that the x gets multiplied by the constant when you find the explicit solution. By the way, you can do y less than 0 in a very similar way for that one. Here's another one. Y is plus x over 2 dy dx. So first of all, I put it in standard form. I calculate the integrating factor as x squared, multiply by the integrating factor, reverse product rule, integrate both sides, answer. It's the same set of steps in every one of these problems, right? Put it in standard form. Calculate the integrating factor. Multiply by the integrating factor. Reverse product rule. And then integrate both sides. This time, I had to integrate e to the minus t times t plus 1, which we know how to do by integration by parts, which we learned so it seemed like a lifetime ago we learned that, but we did learn that. You still know it. Here it is. All right, I'm starting to lose my voice here. So didn't have to be terse. So this one has a constant p, which gives us e to the 4x as our integrating factor. Multiply by e to the 4x, we get that. Reverse product rule. Integrate both sides, and there you have it. All right, then there's one more example. Actually, here's another example. This one actually came with an initial condition, so let's talk about it. So first of all, I put it in standard form by dividing by sine x. Mu ends up being the exponential of the integral of cosine over sine. We make a u equals sine substitution, which gives us the exponential of the natural log of the absolute value of sine x. And so then that gives us absolute value sine x. So if we assume that where sine x is positive, maybe I did something sneakier. Well, anyway, let's assume that where sine of x is positive. If we do that, then we will get to this, which is sine of x dy dx plus cosine of x y equals to x, right? And I don't. There's. Oh, I think this one's got an error. That's supposed to be sine of x. Yeah, I dropped the sine of x there. So that's supposed to be there too. Right, so that gives us y sine of x equal to, not that, no, integral of x sine x dx, which of course we have to make a dv and u, so we get minus x cosine of x plus the integral of cosine x dx, which is equal to minus x cosine of x plus sine of x plus a constant. So therefore y was equal to actually a constant plus sine x minus x cosine x. Hopefully I haven't made a mistake in the integration by parts I just did there, and then I'm dividing by sine x. So I think that would be the general solution. Now I'm told that y of pi over 2 is 2, and if I plug in pi over 2, so I think this is all junk, unfortunately. Sorry guys. But see if I can work it out here. y of pi over 2 equal to 2, so that means that 2 is equal to c plus 1. Cosine of pi over 2 is 0, and sine of pi over 2 is 1, right? So it looks like c had better be 1. So put that back up in there. That gives you the solution there. Well, I'm glad we looked at that one. There's an error in that one. But, you know, I do make mistakes at times, and if you're ever in doubt, you know, send me an email. dy dx equal to this. So I rewrote that as dx dy equals to that. And then, like so, okay, so now it's in standard form. My integrating factor is a function of y in this kind of funny problem because it's got x and y's roles reversed. So e to the minus 2y is my integrating factor, multiply by it, reverse product rule, integrate both sides. Good to go. So, yeah. Anyway, and here's a summary of the method. First of all, put the thing into standard form, calculate the integrating factor, multiply the given standard form differential equation by the integrating factor, group terms, apply the product rule in reverse, integrate both sides, don't forget to add the constant, solve for y. Now step 6 is only needed if we're told to find an explicit solution, alright? And then finally apply the initial condition if you got one. You could do 7 after 5. In fact, sometimes it's much easier to apply the initial condition right after you get done with the integration. Of course, after all of this, you might wonder why on earth did we do this at all? And there is actually a good and satisfying answer to that, but I will leave the differential equations course to explain that to you. So, anyway, I think that's it. I have another batch of homeworks that I don't think I'm going to make a video about, but I'll just tell you that, you know, homework's 10, which has some just general purpose questions about, you know, just some introductory questions about, is this a solution? You know, verify if it's a solution, something like that. This one looks to me like homework 11 that of course I will post if you want to look at and solve. These appear to be all separation of variable problems. Some of them have initial conditions. All right. Yeah. Separation of variables. This one here looks like, yeah, so far separation of variables. This one, oh, yep, still separation of variables. I thought for a second there, I thought it might be integrating factor technique, but separate, you gotta do partial fractions on this one. See, that's the nice thing about this topic, is that if you wanted to test integration technique, you can easily, wrap an integration technique into one of these problems. And a lot of times I'll do that on a final. I'll ask a question which involves separation of variables and an integration technique, because I can do both at once. And I think that ability to solve both of those at the same time is the kind of skill level I'd like to see in a student making a good grade in Calculus 2. This one's really quite different. This one involves a substitution. So I think for you guys this would be sort of more of a challenge problem, but it is straightforward calculus. If you make a substitution, you differentiate it, and then you plug it into the differential equation and work from there. Number 30 is nice. It's this is an orthogonal trajectory problem. So this was a little bit different than the ones I've worked before, but the principle remains the same. Find the differential equation that the given family satisfies, and form the negative reciprocal to find the orthogonal trajectories. And then homework 12. It is, I think, yeah, these are integrating factor problems again. All right. Yeah, integrating factor. More integrating factor. Yet more integrating factor. Now, this 23 is kind of a more exotic thing called a Bernoulli equation. That's just there for breadth. You don't have to work that one if you don't want to. This one's a substitution. Again, I would say that's a breadth problem for this course. 27 is an application to, this is the RL circuit problem again. This is the RC circuit problem for you electrical engineers. Maybe you'd be interested in this. This is Kirchhoff's voltage law for charge. dq dt is the current, of course, and solve this first order differential equation. It gives us the charge as a function of time. And then you can differentiate that to find the current. Notice that as time goes to infinity for an RC circuit, we get current going to 0, which is because after the capacitor is very charged up, after a long time, it behaves like an open circuit, right? All right, let me stop telling you Physics 232 stuff. And then homework 13, there's just a problem here on this population model, and I solved it using the usual separation of variables, it looks like. And we were given some data, so this is actually a rumor mill problem. So I'm solving this interesting applied rumor mill problem there. But anyway, kind of an anticlimactic point to end the course on, but there you have it. Good luck. Thanks.